Process characterization and metrology in semiconductor industry. Process characterization and metrology are essential pillars of semiconductor manufacturing. They ensure that each process step consistently delivers the required quality, precision, and performance. In this highly complex industry, even the smallest variation can affect yield and device functionality. Advanced measurement technologies provide the data needed to monitor and control these processes with high accuracy. Measurement refers to the collection of quantitative data about materials, layers, and patterns formed on wafers. Inspection focuses on identifying defects, particles, or deviations from expected patterns. Analysis then interprets these results to determine root causes, trends, or correlations across multiple process steps. Finally, control involves applying this information to fine-tune tools and workflows in real time or post-process. Together, these four functions, measurement, inspection, analysis, and control, form the backbone of process integrity and enable continuous improvement in semiconductor production. What is metrology? Metrology, the science of measurement, is fundamental to semiconductor manufacturing. It provides the comprehensive techniques needed to quantify and analyze critical parameters at every stage of production. These techniques focus on measuring dimensions such as line widths, feature heights, and critical dimensions, parameters that must be tightly controlled at the nanometer scale. Material analysis includes determining the composition, thickness, and crystallographic properties of each layer deposited on the wafer. Surface metrology addresses roughness and morphology, which influence adhesion, reflectivity, and functional performance. Defect metrology is key for detecting, classifying, and performing root cause analysis on unwanted particles or pattern errors. Metrology plays a critical role in quality assurance, helping ensure that devices perform reliably. It supports process control by enabling real-time monitoring and optimization. Finally, it enhances yield by identifying inefficiencies. With over 400 to 600 steps and features smaller than 14 nanometers, semiconductor manufacturing demands 99.9% accuracy and constant 24/7 monitoring. Core concepts. Core concepts in process characterization center around understanding and controlling the critical variables that influence semiconductor manufacturing. Process characterization involves systematic analysis, starting with parameter monitoring to track key variables throughout each production stage. This is followed by process optimization, where data insights help refine operations for higher efficiency and yield. Statistical control then uses that data to detect trends, minimize variation, and maintain process stability. Central to this framework are critical parameters that must be continuously measured. These include dimensional attributes like width, height, and depth, electrical properties such as resistance and capacitance, optical characteristics, including thickness and uniformity, and material features like composition and purity. Each of these measurable variables impacts device performance and must be precisely maintained. Measurement precision is essential, with tolerances often within plus or minus 0.1 nanometers, underscoring the nanoscale accuracy demanded by today's advanced technology nodes. These principles are fundamental to achieving consistent, high-yield semiconductor production. Why critical? Process characterization and metrology are absolutely critical to the success of semiconductor manufacturing. First, they directly impact quality and yield. Manufacturers aim for over 95% yield, and even a single defect can cost more than $1 million in lost product and downtime. These high stakes make accurate monitoring essential. As technology scales from 3 nanometer to 1 nanometer nodes, precision requirements increase exponentially. Smaller features demand tighter control over every variable, making advanced metrology tools more important than ever. In terms of cost control, effective metrology reduces rework costs by catching issues early, minimizes material waste through precise monitoring, and improves efficiency across the fab. Another crucial factor is real-time control. Continuous 24/7 monitoring and feedback loops allow for immediate corrective actions, ensuring stability and minimizing downtime. Together, these capabilities support innovation, profitability, and competitiveness in a rapidly advancing industry with extremely narrow process margins. Core principles. The core principles of process characterization form the foundation for systematic analysis and control in semiconductor manufacturing. One essential principle is the design of experiments, or DOE, which enables structured, methodical testing. Through factorial design, multiple variables are tested simultaneously to uncover interactions and optimize settings. Response surface methods help map out how changes in process inputs affect outputs, leading to optimal performance. Statistical analysis supports data interpretation and decision-making. Tools like analysis of variance, ANOVA, help identify which factors significantly impact outcomes. Regression modeling provides predictive insights, while confidence intervals define the reliability of measurement results. Another key area is control strategy, which ensures processes remain within specifications. Statistical process control, SPC, helps track variability. Fault detection and classification, FDC, identifies deviations early. And advanced process control, APC, uses real-time data and models to make intelligent adjustments. Together, these principles ensure stability, efficiency, and high-quality manufacturing. Characterization. Workflow. The characterization workflow follows a systematic methodology to ensure reliable and reproducible results in semiconductor processing. It starts with planning and design, where the objective is clearly defined, the design of experiments, DOE, is established, and key parameters are selected. Resources are also allocated at this stage to ensure proper execution. Next is data collection, where metrology tools are employed to gather critical measurements. Quality checks, inline monitoring, and data validation help ensure the reliability of the information gathered. The third stage, statistical analysis, involves evaluating trends, developing predictive models, and conducting correlation and significance testing to draw actionable conclusions from the data. Process optimization follows, where parameters are fine-tuned, recipes are adjusted, and process windows are defined through validation runs. Finally, implementation and control includes transferring the optimized process, setting control limits, configuring monitoring systems, and embedding a culture of continuous improvement to sustain gains over time. Measurement techniques. Advanced characterization in semiconductor manufacturing relies heavily on precise, high-resolution measurement techniques. Optical metrology is a fast, non-destructive method commonly used for rapid assessments. It includes scatterometry, which measures critical dimensions, film thickness, and surface profiles using light scattering patterns. Interferometry is applied to analyze surface height and wafer flatness with extreme accuracy. Reflectometry, another optical method, measures film thickness and optical constants, such as the refractive index, N, and extinction coefficient, K. These techniques offer a precision of plus or minus 0.1 nanometers, enabling tight process control. On the other hand, SM imaging provides high-resolution visualization, ideal for detailed inspections. CD-SEM measures critical dimensions at the nanometer scale. Cross-section SM helps analyze layer structures, revealing insights into deposition quality. Defect review SM supports morphology studies and identifies particle defects or pattern abnormalities, achieving resolutions down to 0.5 nanometers. Together, these techniques form the backbone of precise process control and defect analysis. Measurement techniques. Advanced measurement techniques in semiconductor characterization also include subsurface and atomic scale methods for a deeper understanding of materials. X-ray analysis plays a crucial role in subsurface examination. XRF, or X-ray fluorescence, is used to determine elemental composition with high accuracy. XRD, or X-ray diffraction, reveals crystal structures, which is essential for verifying material phase and orientation. XPS, or X-ray photoelectron spectroscopy, provides insights into surface chemistry, detecting elemental states and contamination. These X-ray techniques collectively enable 3D analysis, revealing depth profiles and buried layer properties. On the atomic scale, AFM, atomic force microscopy, and STM, scanning tunneling microscopy, provide ultra-high precision. Topography mapping with AFM generates detailed surface images. Roughness measurements, such as Ray, RQ, and ARS, quantify texture critical to process control. CD-AFM measures critical dimensions with sub-nanometer accuracy. These tools operate at angstrom-level precision, making them indispensable for nanometer-scale device development and yield improvement. Applications. In semiconductor manufacturing, key applications of metrology focus on critical measurements that support process control and yield optimization. Critical dimension, CD measurement, is essential for ensuring pattern fidelity and device performance with a precision of plus or minus 1 nanometer. Film thickness is another crucial metric, measured with sub-angstrom accuracy, down to plus or minus 0.1 angstroms, to maintain process uniformity. Surface roughness affects interface properties and must be tightly controlled, measured at plus or minus 0.01 nanometers. Overlay accuracy ensures correct layer alignment, with tolerances as tight as plus or minus 0.5 nanometers. These measurements support major process applications, including lithography, where CD, overlay, and line edge roughness are critical. In etch, measurements guide profile control and selectivity. Deposition benefits from thickness and uniformity checks, while CMP processes rely on metrology to monitor planarization and detect defects. A technique. Comparison reveals trade-offs. Optical methods are fastest. SEM offers superior resolution, X-ray penetrates deeply, and AFM gives atomic scale detail. Altogether, over 400 process steps involve more than 600 metrology points, underscoring the complexity and importance of precise characterization. Inspection technologies. Advanced inspection technologies play a critical role in defect detection and quality control throughout semiconductor manufacturing. Optical inspection is ideal for fast, non-destructive screening. It identifies surface particles and scratches, detects pattern defects and misalignments, and reveals line breaks or bridging between features. With a detection limit of 20 nanometers, optical systems offer excellent throughput, enabling real-time monitoring across large wafer areas. Their high speed makes them well-suited for inline inspection without halting production. In contrast, electron beam inspection delivers ultra-high resolution capabilities for submicron defect detection. It's especially powerful for buried layer analysis and identifying voltage contrast defects, which are invisible to optical tools. With a resolution of 0.5 nanometers and ultra-high sensitivity, electron beam systems enable nanoscale precision analysis. While throughput is lower, their ability to detect the smallest and most subtle issues makes them indispensable for root cause analysis and advanced process diagnostics. Together, these inspection technologies ensure comprehensive coverage from surface to subsurface. Inspection technologies. In semiconductor manufacturing, advanced inspection technologies are vital for defect detection and quality control. X-ray inspection is a powerful non-destructive technique that enables 3D imaging to reveal internal voids and cracks that are not visible externally. It also assesses the integrity of wire bonds and can detect package delamination issues. This technique offers deep penetration into the material, allowing for full volume inspection and revealing hidden internal defects. Because of its 3D capability, X-ray inspection plays a crucial role in identifying internal structural failures before they impact device reliability. On the other hand, laser scanning focuses on surface anomalies. It supports real-time monitoring, providing immediate feedback for process control. This method is known for its ultra-fast scan speed and full wafer coverage. Laser scanning excels in detecting surface-level defects and ensuring consistent quality across large areas, enabling real-time process adjustments and reducing yield loss. AI enhancement. AI-enhanced inspection software brings machine learning and next-generation technology to semiconductor manufacturing, transforming how defects are detected and processes are optimized. Advanced pattern recognition uses complex algorithms that outperform traditional inspection methods in both speed and accuracy. These AI systems can identify subtle patterns and anomalies that might be missed by manual or conventional digital inspection techniques. Machine learning adaptation allows the system to continuously evolve, learning from new data and adapting to design changes automatically. This makes the inspection process more resilient and responsive to shifting manufacturing needs. Real-time processing delivers immediate feedback, enabling corrective actions to be taken instantly, which minimizes scrap and delays. Predictive analytics further strengthens this capability by forecasting potential defects before they happen, allowing for proactive maintenance. With system integration, manufacturers gain 40% better accuracy, 60% fewer false positives, 300% faster processing speeds, and 50% less downtime. These innovations support Industry 4.0 goals and enable 24/7 operation with a 99.9% detection rate. Key parameters. In semiconductor manufacturing, controlling key parameters with extreme precision is essential to ensure device performance and yield. One of the most critical measurements is the critical dimension, which refers to the precise control of line widths on a chip. It supports feature width control, ensuring that each transistor or interconnect matches design specifications. Gate length optimization is another major focus, as it directly impacts the speed and power efficiency of the device. Accurately measuring contact hole diameter is also necessary to maintain connectivity and reduce resistance. Together, these parameters require a measurement accuracy of 99.5%, reflecting the industry's demand for near-perfect dimensional control. Equally important is film thickness, which must be managed at the atomic level. Monitoring the oxide layer is critical for gate dielectrics, while precise control over metal film deposition ensures proper electrical conductivity. Dielectric thickness measurements support insulation and performance. With 98.8% uniformity control, these layer-by-layer measurements are foundational to reliable semiconductor fabrication. Key parameters. Two critical parameters in semiconductor manufacturing are surface roughness and overlay accuracy, both of which directly affect device performance and yield. Surface roughness measurements, defined by raw, RQ, and RZ values, quantify the smoothness and texture of wafer surfaces. These metrics are essential for CMP quality control, ensuring that planarization processes remove excess material evenly. Roughness also impacts interface analysis, particularly where different material layers meet, and plays a major role in overall wafer surface quality. A high surface quality rating of 97.2% indicates excellent process control during polishing and deposition steps. Overlay accuracy measures how well different layers of a chip are aligned, with registration error being the key indicator. Achieving precise layer alignment is essential as transistor and interconnect layers stack up. Pattern registration ensures each lithography step is correctly placed, while multi-layer stack alignment becomes increasingly important with advanced nodes. An alignment precision of 99.1% reflects the tight control required in photolithography to maintain device integrity and functionality across billions of transistors. Process applications. Process applications in semiconductor manufacturing focus on controlling key parameters at every step to ensure precise and repeatable outcomes. In lithography control, CD, or critical dimension, control is vital for ensuring accurate feature sizes on wafers. Parameters like line edge roughness, LER, and line width roughness, LWR, are closely monitored with typical values reaching 2.5 nanometers and 2.8 nanometers at 3 sigma, respectively. These measurements help manage variability introduced during the lithographic patterning process. Additionally, mask error enhancement factor, MEF, typically around 1.5x, quantifies how variations in the mask pattern impact printed dimensions, helping to refine mask and process design. Overlay, OVL accuracy, is equally critical for ensuring each new layer aligns perfectly with the underlying patterns. Etch process control focuses on sculpting patterns with extreme precision. Profile angle, maintained within plus or minus 2 degrees, ensures sidewalls are vertical and consistent. Etch selectivity, such as 100 to 1 dar, reflects the ability to remove one material while leaving others intact, crucial for protecting underlying layers. Etch rate uniformity, controlled within plus or minus 3%, guarantees consistent processing across the entire wafer surface, minimizing variation and maintaining high yield. Process applications. In semiconductor manufacturing, deposition and chemical mechanical polishing, CMP, play critical roles in meeting strict process application requirements. For deposition and CMP, thickness uniformity is essential, with a target of plus or minus 2%. This ensures even layering across the wafer, which directly affects device performance and yield. Step height control must also be maintained within plus or minus 5 angstroms to achieve precise topography and layer integration. Surface roughness should be as low as 0.2 nanometers to support high-quality interconnects and reduce variability. Planarization efficiency needs to exceed 99% to ensure a flat surface for subsequent process layers. On the performance side, measurement repeatability must reach 99.8% to guarantee consistent data collection. Process control capability is quantified using CPK, and it must exceed 1.67 to signify robust, capable processes. Yield enhancement of over 15% reflects improved product output and reduced defects. Achieving this requires over 600 metrology points across a 400-step flow to maintain process insight and quality control. Current challenges. Semiconductor metrology is facing critical barriers as the industry pushes toward ever smaller nodes and increasingly complex structures. One of the primary limitations is node scaling limits. As feature sizes shrink, the physical boundaries of measurement techniques are tested. These limitations have a critical impact, making it harder to maintain precision in smaller geometries. At the same time, precision demands are rising. As atomic-level accuracy becomes the norm, measurement tools must detect changes in dimensions as small as fractions of an angstrom, which increases both technical complexity and cost. Another major challenge is 3D structure complexity. With advanced devices like FinFETs and gate-all-around transistors, multidimensional measurement becomes essential. Capturing accurate topography and depth is more difficult, leading to high impact on process control. Lastly, there's a persistent speed versus accuracy trade-off. Process monitoring must be fast enough to support high throughput, yet accurate enough to catch tiny deviations. Balancing both is a continuous challenge for metrology engineers. Emerging solutions. To address metrology challenges in semiconductor manufacturing, several next-generation technologies are emerging. AI-enhanced metrology represents a major breakthrough by leveraging machine learning for unprecedented measurement accuracy. These models can identify patterns, reduce noise, and correct for systematic errors, enabling atomic-scale precision. This is transforming how data is interpreted across complex wafers. Meanwhile, real-time control has already been implemented, allowing process adjustments to be made instantly during manufacturing. This capability improves yield, reduces variation, and enhances equipment efficiency by closing the feedback loop on the production line. Another advancement is multimodal fusion, which combines data from various metrology sources, optical, electrical, and structural, to form a comprehensive process understanding. This integrated approach leads to more robust insights and better decision-making. Finally, predictive analytics is an emerging area focused on improving yield by forecasting defects or failures before they occur. Using statistical models and historical data, manufacturers can intervene proactively, boosting both quality and productivity. Future roadmap. The future of semiconductor metrology is rapidly advancing through staged innovation. From 2025 to 2027, we are witnessing the AI/ML revolution, which is already 85% complete in implementation. This phase includes autonomous defect classification systems that can detect and categorize issues without human intervention. Self-learning measurement systems are being developed to adapt dynamically to new structures and data. Additionally, predictive process optimization is being enabled through AI, helping fabs adjust parameters before problems occur. From 2028 to 2030, quantum metrology is projected to emerge, currently in the research phase with 30% progress. This includes quantum-enhanced sensing, subatomic precision measurement, and quantum error correction, all promising unprecedented accuracy in nanoscale environments. Looking beyond 2030, the vision is fully autonomous fabs. These will feature lights-out manufacturing, where operations occur with zero human presence. Digital twin metrology will create virtual models for real-time optimization, and the ultimate goal is zero defect production. This roadmap defines the future trajectory of semiconductor process control. Key takeaways. Metrology is now a mission-critical function in semiconductor manufacturing, with hundreds of steps per chip requiring precise measurement. It underpins every advanced process node, from 3-nanometer logic to quantum devices. Without accurate metrology, process control collapses, yield drops, and scaling halts. As devices become more compact and complex, metrology becomes the backbone of reliable production. The future is shaped by an AI-driven transformation. AI targets ultra-high accuracy, enabling real-time predictive metrology. By shifting from reactive responses to proactive corrections, machine learning models are redefining how data is used in fabs. This allows earlier defect detection and smarter decision-making. There is also a precision evolution underway. We're reaching atomic-level accuracy, pushing the limits of classical physics. Revolutionary techniques are required to measure at these scales, demanding innovation across hardware, software, and algorithms. Finally, industry transformation is enabled through advanced metrology. By improving yield and reducing variation, metrology fuels the continuation of Moore's law. It supports the transition to new architectures and ensures competitiveness across the semiconductor ecosystem. Strategic investment. The future of semiconductor metrology hinges on strategic investment. As we approach 2030, the global metrology market is projected to experience significant growth, driven by increasingly complex process demands. With continued node scaling and the emergence of new device architectures, sustaining innovation is not optional. It is essential. The ability to measure, monitor, and optimize at atomic and quantum scales requires constant advancement in tools, software, and integration strategies. Meeting these scaling challenges will demand long-term investment in R&D, infrastructure, and talent. Companies that prioritize metrology innovation will maintain a competitive edge through enhanced yield, faster time to market, and greater reliability. The closing message is clear. The future of semiconductor manufacturing depends on metrology excellence. Precision measurement drives technological breakthroughs, fuels competitive advantage, and underpins every step in the process. With sustained focus and collaboration, the journey towards smarter, faster, and more autonomous fabs will continue to accelerate.